Today I'm starting with Intel data parallel extensions for Python. My name is Riccardo Balin, and I'm a assistant computational scientist at ALCF. Um, if you have questions, feel free to put them in the Slack channel for the workshop or put them on the chat here in the Zoom, and then we'll try to get to them later when we'll probably try to do a couple minutes break between the different topics. So first off, maybe actually I should confirm. Can everybody see the screen and can hear me? Okay.
If you can see your screen and hear you okay.
Okay, great. Thank you. Um, so data parallel extension for Python, or shorthand is DPEP, is really Intel's Python stack for programming on generally heterogeneous devices, but this really includes Aurora CPUs and GPUs. And it's composed of three packages that we'll walk through today. The first is DPNP, which stands for Data Parallel Extension for NumPy. Second one is DP Control, which stands for Data Parallel Control. And then finally, Numba DPEX, which is the Data Parallel Extension for Numba. The overarching programming model for all of these different packages is what Intel calls compute follows data. And what this means is that the offload target is actually inferred from the input arguments to the library call or the kernel call. So when you call a particular function, or if you make a kernel in NumPy and then you launch it, you don't have to specify what device that kernel runs on each time, or even any time that you run the kernel. That is actually inferred just on the input data. And so, for example, just a very simple few lines of code, in this case using DP control, we can see that we first create an array x GPU, and here we do specify that the array should be allocated on the GPU, but then we call the function dp.square. We don't have to specify the device. And actually, then if we want then to print the device of the output, we see that that's actually also on GPU, in this case GPU 0, because the output data is also consistent with the input data. And so that will be resident on the device if the input data is on the device, or the same device as the input data. So that could be CPU or GPU. Now, how do you access these DPEP packages on Aurora? For DPNP and DB control, it's very easy. These are included in the base AI ML frameworks Conda environment. So all that users need to do is module load frameworks that you see here. And then if you want to run this Conda list command and grep for the particular packages, you should see both DP control and DPNP and the respective versions that are currently installed and available with that module. But unfortunately, Numba DPEX is not part of that base module, so it does require a few extra additional steps in case you want to use that package. The documentation has a lot more detail on this, but this little box basically summarizes what needs to be done, which is really you still load the frameworks module and get the base environment. At this point, you can either clone it or you can create a new one, and then you follow these steps to install the dependencies that NumPy has, and then you need to install NumPy from source. So you clone the repository and then run this last command here to install it. Now, let's go through those actual packages. So we'll start with DPNP, which again is the data parallel extension for NumPy. And so this is really what Intel did to implement a subset of the NumPy API using DPC++. So it was intended as a drop-in replacement for NumPy, so in this spirit, it's very similar to what CuPy did for CUDA devices, in the sense that it's a drop-in replacement in many cases for NumPy on NVIDIA devices. And so it's really the first, I would say, the first step in porting NumPy code or CuPy code to the Aurora GPUs. And this really should be a drop-in replacement. So instead of writing import NumPy as NP, you could do import DPNP as NP, or similarly with CuPy. But we do encourage users to check this comparison table, and there's a link here in the slides to make sure that the API, either NumPy or CuPy that you're interested in, are actually covered by DPNP. Intel has pretty good coverage at this point, but is still improving their coverage and will keep making improvements throughout this 2025 year. And so, if you don't see an implementation of a particular API that you're interested in, let us know, and we can definitely try to work with Intel to accelerate that specific function or functionality that you're after. I also wanted to mention that it does support reduced precision for floating point, complex, and integer numbers. So, for example, you could go all the way down to FP16, int 8, and then for complex numbers, you can only do complex 64. So that would be two FP32 numbers. But again, the comparison table and then the documentation will specify exactly what is supported for each function. And then lastly, keep in mind that it does use 1MKL in the background when it can. And so, for example, mapmult computation with DPNP is actually very efficient on the Intel GPUs because it does leverage 1MKL. So again, just a very simple example, really just to highlight some key features. This is just a simple sum. Um, but I do wanted to highlight a couple lines of code here. The first is that you can see again we're allocating an array, and in this case we're actually not specifying any device. So x is just equal to np dot as array, and then this simple array here. So we don't actually have to specify where we want this array to be because the default sickle device on Aurora are the GPUs. And so we can be specific, but also we could leave that out if we wanted to. The other thing I wanted to mention is that when we allocate an array with DPNP, a sickle queue and then a device object are created when you create the array and then are carried along with the array. What that means is that if you're trying to access a particular device associated with an array or a sickle queue associated with an array, you can query that by just doing x.sicklequeue and x.device. And that's helpful sometimes, and we'll see when it's helpful a bit later on. And then finally, again, reiterating the compute follows data programming model, you'll see that we call np sum on x, again, without having to specify a device. And this kernel or this function is actually submitted to the queue of the input array x. And then similarly, y is created on the same device as x and also is associated with the same signal queue as x. And again, we'll see the use of queues a bit later on. But in terms of the output, just to validate, you can see that both the input and output arrays are both on the same device, in this case, GPU 0. A couple more important details. The array creation APIs in DPNP all take, they take multiple arguments, but three that are important are the device, the USM memory type, and the sickle queue. So for example, this allows you to actually allocate an array on any device that you want. So for example, if you wanted to target specifically GPU 1, in this case, this is actually the second tile of GPU 0. Or the 0th PVC on the Aurora nodes, you would just specify that with this string right here. You would allocate the array and then set the device equals to GPU colon 1. Similarly, if you wanted to allocate the array on the USM, you could do that too by specifying that you want the shared USM memory type. USM type takes other arguments, such for example, host or device. The default is actually device, so it'll always allocate on the device unless you tell it not to. The other thing is that on Aurora, the only sickle devices that are visible are actually the GPUs. So this one API device selector environment variable is set to level 0 colon GPU. So that means that actually by default, you cannot allocate arrays with something like DPNP on the host. But you can just modify this environment variable to include not just level 0 colon GPU, but also the string OpenCL colon CPU. And when you modify this environment variable, then you can access with DPNP all the sickle devices that are available. So that includes the host and then the 12 tiles on the node. And you can play with this environment variable. So if you wanted DPNP, for example, to only see the hosts, the CPUs, then you would just use this OpenCL semicolon, yeah, colon CPU string here. And then lastly, an important detail to keep in mind is that from version 0.15.0, so this includes what is available on Aurora today. DPNP is run, all the kernels are launched asynchronously with linear ordering, which means that sort of one is launched right after the other in the same sequence that you have in your code. And this is also similar to CuPy, so it should be familiar if you're coming from NVIDIA GPUs. But what this means is that when you're trying to time kernels, you need to make sure that you're waiting for the kernel to actually finish. Otherwise, you are probably just measuring the kernel launch time. And for DPNP, this is done by accessing the SQL queue and then calling wait on that SQL queue. So in this simple map mult example, we can allocate an array and then we do a map mult between just two copies of that array. But then if we want to time this map mult operation, we actually need to wait on the sickle queue of the output so that we make sure that the map mult operation is done running. Okay, now DP control. This is a library that is complementary to DPNP, but it's really sort of intended for users to access all the devices supported by the DC++ runtime and expose features such as device introspection, creating specific queues, or the memory allocation types. There's objects for defining memory allocation and kernel creation from OpenCL code. So this is really intended as a way to effectively enable to Python programmers the ability to understand what devices are available, what memory types are available, and then really have control on the devices and the queues that kernels are executed on. DP control also provides this tensor library that is in a way very similar to DPNP. So there's a lot of overlap here. Perhaps the key here that is it follows the Python array API standard. And so we'll see later, this is really important to provide interoperability through DLPack to things like PyTorch. This API provides similar array creation, manipulation, and linear algebra functions to DPNP. So again, there's overlap and users can choose to use either or. And it supports similar precision. So actually what happens is that DP control is actually a dependency of DPNP. So DPNP uses a lot of features within DP control. So we wanted to go through a couple key examples just to show users how you might do some basic device introspection or node introspection. So here is that simple example. You would import DP control, and then, for example, you can get the number of available devices by filtering with a specific type of device. In this case, we filter by GPU. We can also get the devices as a list, again, filtering by type, in this case, GPU. And so then this device list allows you to loop over the devices and print information, for example. And then you can also query, for example, if the CPU device is visible. And so when you run this little snippet of code, what you see is that on an Aurora node, you actually find 12 GPU devices. This is really because the frameworks module sets the ZE flat device hierarchy flag to flat, which exposes all the 12 tiles as individual devices. You can change that by changing this environment variable to composite, in which case you would see now 6 devices with 2 subdevices each. And then finally, so you can see here we are printing the information for all the 12 devices. Pretty standard. It's a SQL device with a level 0 backend, device type GPU, and these are Intel data centers GPU Max 1550. And then lastly, as I mentioned earlier, by default, you actually don't see the CPU devices or a host. And that's due to that one API device selector flag being set to default to level 0 GPU. But of course, you can change that and then access the CPU. But DP control allows you it gives you the function so that you can actually make sure that all the devices that you're after are visible. And Once you know that they're visible, the next thing you can do in this other snippet, code snippet, is that you can create queues for each particular device. So for example, in this case, we're using a combination of DPNP and DP control to first get a list of devices. And then what we're doing in this first highlighted box is we're creating a sickle queue for each of the devices specifically, and then storing them in a list called underscore queues. And then we define a very simple function which takes in a device ID and then allocates an array with DPNP based on a specific queue, and then that queue is indexed on the device ID. And so then the last couple lines, what those are doing is are just iterating over all the devices, and then are allocating an array on all the devices based on these queues that we first created. And so you see here, if we take a look at the output, we see that we created one array on each of the 12 devices. So again, DP control and DPNP really work together to allow you to DPNP really do sort of traditional linear algebra or sort of array manipulation and array creation. But DP control allows you to sort of give you the fine-grained control if you want in terms of where these kernels run and what queues these kernels are run on. And something to note is that you can create multiple queues for the same device. So you can, in that way, have the control that Sickle would give you, but from Python. And then finally, NumPy is the last package of the three. So if you're familiar with NumPy, this is pretty similar. It's just an extension that Intel developed so that you could generate performant and parallel code with NumPy, but accessing Aurora CPUs and GPUs. Something that they developed, which is somewhat new, is what they call this kernel programming API, which is integrated with an LLVM-based code generator. And NumPy really integrates well with NumPy, DPNP, and DP control. So we'll see an example later how you are basically creating arrays with DPNP and then feeding those into NumPy kernels. And again, it follows the compute follow data programming model. Something that we won't go into too much detail of is the different types of kernels that you can create with NumPy, but there's links here so users can follow up and take a look at the documentation. I'll just show a simple example of a range kernel later on. But something to know, which is pretty useful, is that you can create device callable functions. So these can be invoked in different kernels or within different device functions later on. And then finally, the math and DPNP packages are supported within NumPy kernels. But again, please refer to the documentation because not all math and DPNP functions are supported. And then also the documentation specifically has information on the data types that are supported for these different functions. So this is just a simple range kernel to highlight some of the basic details on creating NumPy kernels. And a range kernel is really just a basic parallel for calculation, ideally suited for things like embarrassingly parallel kernels. So such like an element-wise computation. And so here we're doing, again, just a simple sum. But except for sort of the importing lines that you see above, as you might expect, you need to decorate kernels, and so that's done here with this at depex.kernel. And then the thing to note is that the kernels that you create need to have as a first item this KAPI item. This is a work item class that this kernel API that Intel developed provides. And then it's what you use within the kernel to actually access the particular work item and therefore subdivide what work or what parts of that array this particular work item is working on. And so you can probably see from this little code that NumPy follows the SPMD programming model. So as I mentioned, each work item runs this particular function that you define, but on a subset of the elements of the input array. And so lastly, at the bottom, you see, as I mentioned earlier, that it integrates well with DPNP. So we create three arrays, two are inputs, one are output with the DPNP. And then we call the kernel at the bottom with depex.kernel, call kernel. And then here, the main thing to point out is that you have to specify the function name, the kernel name, but also the set of work items. So this is the range of work items that are going to be used to parallelize this kernel on the particular input data that then you provide later on in the function call. But again, please go back to these links to sort of go into more details just for the sake of time and space. We're not going into all the different types of kernels that users could create. Um, Finally, we just wanted to point out that there is interoperability through DLPack. What this means is that using DPNP and DP control, you can effectively do zero copy data accesses on both CPUs and GPUs with NumPy, of course, that's CPU only, and then PyTorch, but unfortunately not with TensorFlow. This is actually due to um, the fact that TensorFlow doesn't seem to follow the same, it's not up to date with the same array API standards. And so some of these from DLPack or to DLPack operations don't actually work, unfortunately. But again, this is a very simple example to show how you can create a PyTorch array and move that over to the GPUs. And then you can call DP from DLPack to create a DPNP view of that array. And then if you modify the PyTorch array, you can then see in the output log that both arrays are on the same device, and they actually, even though you modified just one of them, they both are the same because DPNP is just a view of that PyTorch array. So it's not actually creating a new one. And so that's going to be really useful if you're trying to do mixed workloads that do both DPNP or DP control and Numba DPEX, and then you want to integrate PyTorch in there as well. So that's the last slide I had. So I wanted to thank you for your time. And please, if you have any questions, please send an email to our support or even contact me on Slack throughout the next few weeks during the hackathon. And then also here is also the link on where you can find all the little code snippets that I presented, as well as scripts to set up the environment or clone the base Conda environment, then install Numba DPEX. Everything that I talked about today is going to be at this link. So maybe I can stop here and see if there's any questions specific to this DPEP set of packages. And then we'll move on to the iframeworks next.